Hello everyone, welcome to my video on the derivative. Today we're going to learn one of the most important notions of Cal 1, and we're going to build it from the idea or the notion of a rate of change. So let's take a look at this graphically and get some intuition. So let's say I have a graph, this is my x-axis, this is my y. Let's draw a function in green. So let's say I have some function that looks like this. Okay. Let's take a point here, let's call it A. And we'll take this point here, we'll call it B. So at point A, capital A, let's say the x value is little a. Okay. And if the green function, let's call it f, then the point A, we could think of it as little a, comma, as a coordinate point, little a, comma, f of a. Okay. And to find point B, what we could do is shift from A. So add a positive value from A to get to B. And let's call that positive value h. So if we shift over, try it again. If we shift over from A by a value of h, this is going to be the x value of a plus h. Okay, so we're just shifting over by h. And that would cause, so the x value here would be a plus h. And that would cause the y value over here. So let's call this f of a. And this value here, if we go hit the y, would be f of a plus h. Okay, so this is f of a plus h in the big brackets. That's point B. And let's draw a line connecting these 2 points. So the line's going to be in red, going through A and B. This line here in red, we call it a secant line. Okay. We're going to see how this relates to the derivative, but let's go ahead and find the slope of a secant line. So how do we do that? We know how to find the slope of a regular line from high school. The formula that we've seen is m or a, or if you use the letter m, that's fine. You can use m, not to use the same a because these are different a's. So I think I'll stick with m. And we have either rise over run. I'm not sure how you guys learned it. Rise over run. There's delta y over delta x. That's another way. Or the way that I learned it was y2 minus y1 over x2 minus x1. Okay. So let's change the form. So let's look at our point here. If we look at our point A, we call this our first point. Our little a is x1 and our f of a is y1. And this point B here, this would be your x2, y2. And let's plug it into this formula. We plug in our coordinate points. What we get is y2 is f of a plus h, and our y1 minus y1 would be, in this case, your f of a. All that divided by x2 minus x1. Our x2 in this case is a plus h, minus our x1, which is in this case our a. If we simplify this, notice the top, there's nothing we could do. But what we get is f of a plus h minus f of a. All this over a plus h minus a. Notice that the a's cancelled. This is positive, that's negative. He's also, all we're left with is h. Okay. So this over here has a special name. This is called the quotient difference. Actually, it has many names. In physics, we call this the average velocity, also called the average rate of change. But us, we're going to refer to this as the slope of the secant line. So this is stuff we've seen in high school. Not too difficult. You're just finding the slope of a line given 2 points. We're accustomed to this. We know how to do this. So this is specifically looking for the slope of a secant line, and you can find the equation of a secant line y equals ax plus b. But this is how we would find the slope, this formula here. Okay. So here, what we want is a tangent line. We want this red line to touch the function at exactly 1 point. How could we do this? Well, the idea is we're going to take our h value here and make it as small as possible. Make this arbitrarily small, but not equal to 0. But some number that's very close to 0. And how do we do this? By involving limits. We're going to take this value h super close so that b gets extremely close to a, and it's touching at 2 points, but the 2 points are so close to each other that it's essentially touching at a single point. And that's the definition of a tangent. It's touching the function at exactly 1 point. So we're going to use the notion of limits to get this. So let me redraw this. So we no longer have b, and we're dealing with a tangent line. So this red line here is touching the function at exactly 1 point at a. Okay, so this is now a tangent line. Okay. And let's erase this. And we made h essentially very small. So we're taking this definition, this slope, and the equation of our tangent line. So this is the slope of the secant line, not the equation, sorry, the slope of the tangent line is essentially the exact same formula here, but taking the limit as h gets extremely small and close to a. So we'll call this slope of tangent line. Let's call this m tangent. The slope, we'll use the letter m to denote the slope, and we're talking about the tangent line, not the secant line. And it's the limit as h tends to 0, so as h gets really small, of this function, the quotient difference, f of a plus h minus f of a, all this over h. Okay, so this is our definition. So this is the slope of a tangent line at a given point a, at specifically a. Okay. And this is our job. We're going to go ahead and solve for this using our limit definition. Okay. So the limit that we saw in the previous demonstration or illustration shows up very often, and we put a name to it. This is what we call a derivative. So the limit definition of a derivative of a function f at a given number a is denoted by f prime of a. This is the notation we use, f prime. So this is essentially an apostrophe here of a equals the limit as h tends to 0 of f of a plus h minus f of a, all that divided by h. There's a different form. We could also write it as limit as x approaches a of f of x minus f of a over x minus a. This is a second form. This is the one that we commonly use, the one that's boxed, but you could also use this definition. They're equivalent. Okay, and notice that it's the same form of y2 minus y1 over x2 minus x1. Same concept. Okay, so this is our definition. Let's take a look at a couple of examples. Another thing I want to just mention is the notation. So we could write this as f prime of x. This is one notation. Another notation for derivative. So this is our notation. These are all interchangeable. You could write dy dx. What else do we have? We could also write it as y prime. And I think these are the main three that I'll stick to. Okay, so these are the different notations. There's more that I can mention, but these are the main three that I'll stick with. Okay, so these are interchangeable. So instead of f prime of a or f prime of x, I could write dy dx, the derivative of y with respect to x, or y prime. And sometimes y prime we could put an x in brackets like this. Very similar to this, but without the x in brackets, because it's single variable calculus, so we're for now we're always deriving with respect to x. This is going to change later on in the semester. Okay, so this is a different notation. Let's take a look at a couple of examples and how to apply this formula here. Okay, so in this example here, it asks us to use the limit definition. This is important. It's asking us to use the limit definition of a derivative to find f prime of x. So, do you remember the formula for the area of a circle? The area of a circle is pi r squared. Let's consider it a function equivalent. So let's call f of x. Let me do it here. F of x equals pi. Instead of r, I'll use the letter x. So pi x squared. And we consider this function here. Let's go ahead and find the derivative. This is also sometimes called the four-step procedure. I won't refer to the four-step procedure. We're just going to go ahead and find the limit. But maybe on the side, it is a good idea to go ahead and find the composition. This is where students struggle with the most. It's the composition part. So, as always, first thing to do, write down the formula. So f prime of x is equal to the limit as h goes to 0, f of x plus h minus f of x, all this over h. So notice now the definition is slightly different. I used the parameter a because we were finding the derivative at a given point. But here, if we consider all the points on the interval, we just create this function here for all numbers, all a values, and we just call it x. Okay, so this is the definition we're using. So f prime of x equals limit as h approaches 0 of f of x plus h minus f of x, all that divided by h. Okay, so this piece here is probably the one that you're going to want to do on your own, the f of x plus h. So on this side, you could go ahead and try to figure that out. F of x plus h. How do we do this? So a side note, f of x equals pi x squared. Essentially what you're doing is whatever's in the brackets, you're putting it here, you're squaring it, and then you're multiplying it by pi. So if you're looking, let me just make something up now. For f of, I don't know, a heart, the idea of composition, we're going to use this symbol, it's a heart. What you're doing is you're taking the x that's here and you're just substituting it here. So you're squaring the heart, we're going to square it, and then in the front we're going to multiply it by pi. This is the idea of composition. So whatever's in the bracket just goes here. Okay. So this is a way to think about it. So in this case here, we don't have an x in the bracket, we have an x plus h. So how do we rectify this? How do we solve this? Same idea. Whatever's in the bracket, we're just going to square it, and then in the front of it, we're going to multiply it by pi. So we're going to have x plus h in brackets squared, and then times pi. Same idea. Whatever's in here, we just moved it here. We squared it and then multiplied it by pi. This is the composition. Okay. So once you have this part done, the rest is just computational. So we take the limit as h goes to 0, so keep writing the limit in front. F of x plus h, we solved for it, we wrote it this way, so we have pi x plus h squared minus f of x, which is already given. F of x is just pi x squared. All this divided by h. Okay, and now we solve. So the first thing is that we have brackets here, so let's expand it. Very common mistake, try to avoid this. Teachers do not like this mistake. X plus h squared is not x squared plus h squared. Very common mistake. Okay. X plus h, which is a binomial, there's two terms here, it's squared. Remember, multiply it by itself. So x plus h times x plus h. And now it should be clear what to do. We have to FOIL. Okay. So just be careful for that. That's a common mistake that I've seen. So if we expand this out, we get x times x, which is x squared. X times h is xh. Then we have two of them, 2hx or xh, doesn't matter the order. And then h times h, we have h squared. Okay, so this is this guy expanded. I skipped this step where you have to add the two middle terms, but it works out to be the same. Now we have the limit as h goes to 0. We have the pi in the front, x plus h squared, we expanded it down here, which gives us x squared plus 2hx plus h squared. Let me fix that. Minus the pi x squared here. All this over h. Continuing here, keep running the limit. Don't forget to write it. Limit as h goes to 0. We're going to distribute the pi, giving us pi x squared plus 2 pi hx plus pi h squared minus pi x squared. All this over h. So notice that we get pi x squared and then minus pi x squared. So same numbers, opposite signs, they cancel. And we're left with the two middle terms. What we could do here now, and this often happens, we have to cancel out this h, because if we substitute the h now, we're going to get, there's a h on top, we're going to get 2 pi times h, which is 0, times x. So this whole term, because it has the h, which is being replaced with 0, is going to be 0. This has a h as well, it's going to be 0. So you have 0 plus 0 divided by 0. You end up getting the indeterminate form 0 over 0. This is where we have to use our notion on limits, is when we have 0 over 0, we have to cancel out one of the terms. In this case here, it's factoring. So what we could do here is factor out a h. So this term here has 1h, this term here has 2 h's, so we'll factor out 1, that's the GCF. And if we factor out a h here, we're left with 2 pi x. And if we factor out a h here, we're left with plus pi h. Okay, all the other terms were cancelled, and this is going to cancel with the h on the bottom. Okay. If you're not too sure what went on here, just double check your work by multiplying your h back in to see if you get back what you started with. Okay. So here the h is cancelled, you're left with limit as h goes to 0 of 2 pi x plus pi h. And now if we substitute the h, we don't have 0 over 0 anymore, it's not an indeterminate form, so we're okay. The h, this is being replaced with 0, this is gone, pi times 0 is 0, so we're left with 2 pi x. And this is interesting because this is our derivative, this is our answer. And if we replace the x with the r initially, we had said that this is the area of a circle. What we get here is 2 pi r. And this should ring a bell. The derivative of the area of the circle ends up being the circumference of our circle. Okay, so this is a nice application, and this is also true not for every shape, but it's true for volumes as well. If you take the volume of a sphere and you take its derivative, you end up getting the surface area of the sphere. So these are cool applications. You could try it to see it on your own. And let's keep practicing and looking at more examples. Okay, so in this example here, it asks us to use the limit definition. So again, this is important. We're using the limit definition. At this point, this is the only definition we know, but we will see other methods to find the derivative. But here specifically, we're using the limit definition to find the slope of the tangent line at this point here, 5 and 1, given the function f of x equals 1 over x minus 4. Okay, so we have to go to our definition. What's the slope of the tangent? So the slope of the tangent, we'll call it m tangent, is the limit as h tends to 0 of, we could also call this actually f prime of a. Okay, so because we're taking the derivative at a given point, we could bring back the f prime of a. So we're taking the limit as h approaches 0 of f of a plus h minus f of a, all this over h. Okay, so the issue now is what's the a? You could do this in two steps. You could replace this with x's and take the derivative first and then substitute the a. So it's really up to you how you think about it. I think I'm going to go ahead and do it that way. I think it's simpler to do it step by step. So this is f prime of a, but let's go ahead and just take the derivative and then we'll worry about what the a is. So I'm going to replace this with x. It doesn't really matter which way you do it. What's important to figure out is what the a is. So what's the x value? at what value are we taking are we looking for the tangent line? And it turns out to be that our a is the x value of this point. A is 5. This 1 over here is just extra information, we don't really need it. If we were asked to find the equation of a tangent line, then it's different, which we'll see soon. But right now it's just asking for the slope, so all you care about is the a, which is the x value in the point that's given, which is in this case 5. Okay, but we'll come back to this. Let's just go ahead and use the limit definition to find the derivative first. So we have f of x is 1 over x minus 4. Let's go ahead and find our f prime of x. So let me take out the a for now, and we'll do the x first. Okay, so this is still the tangent. So let's go ahead and take the limit. Or maybe on the side, let's go first find the f of x plus h. F of x plus h, remember this composition, we're substituting the x plus h into our function. So in our function now, it's the x is down here on the denominator. So we're dividing by x, and then we're subtracting it by 4. So whatever's in the bracket, it's going to be on the denominator. And we're subtracting it by 4. So x plus h minus 4. Okay. Notice that the x that was here was essentially just substituted here. But instead of x now, we have an x plus h. So the x plus h gets moved here. That's the idea. So the x plus h comes here. That's this term here. Let's go ahead and solve it. So we're taking the limit as h goes to 0. F of x plus h is 1 over x plus h minus 4 minus 1 over x minus 4, all this over h. So again, these are just a bit computational. The next step here, if we focus just on the numerator, what you notice is that you have a fraction subtracted by a fraction. So whenever you're subtracting or adding fractions, our goal is to find a common denominator. Okay, so one way of doing this, a formula you can remember, is if you have a over b plus minus c over d, this is always equal to ad plus minus cb, or bc, doesn't matter the order in which you multiply, over bd. Okay, so you can do this, use this formula here, and that's what we're going to use now. So this is saying multiply a times d. In this case, our a is the 1 multiplied by the x minus 4. So don't forget to write the limit as h goes to 0. So here we're going to multiply x minus 4 on the numerator here. So we get x minus 4 on top, minus, and then we're going to multiply this whole thing here on this numerator. So x plus h minus 4 times 1 is just x plus h minus 4. And then we're going to divide it by the denominator, which we're multiplying, because it's b times d. So this whole thing, if it helps, put it in brackets, and then you multiply it. I'm not going to distribute it, I'm just going to leave it as is. I think it's easier to do it this way. X minus 4. Just keep it in brackets, don't distribute this. Okay. So we use this trick, and then we divided it all by h. Okay. This h on the bottom, you could think of it as h over 1. So again, you have a fraction. This whole thing on top is a fraction divided by another fraction, h over 1. You could think of it as a fraction. How do we divide fractions? If you have 1 over 2 divided by 3 over 4, the way we do this, especially if you can't use a calculator, you're going to have to know that you multiply by the reciprocal. That's the fancy terms. At the end of the day, what that means is that you keep the first fraction, the 1/2 stays, your division turns into a multiplication, and you essentially flip the second fraction. So instead of 3 over 4, it becomes 4 over 3. Okay. And now to multiply, we know how to multiply. You just 1 times 4 is 4, 2 times 3 is 6, and you can reduce. Okay, so just keep this in mind. Whenever you're dividing fractions, because this comes up often, you have to multiply by the reciprocal. You flip the second fraction and turn the division into a multiplication. And that's what we're going to do here. Okay, so this becomes the limit as h tends to 0 of, I'm going to just distribute the negative on top since we're here. So we get x minus 4 minus x minus h plus 4. All this over this part I'm going to leave. So I'm going to leave it as x plus h minus 4 times x minus 4. And then I'm going to multiply it by, here on the bottom, it's h over 1. As we said before, we're going to multiply it and flip it. So h over 1 turns into 1 over h. Okay. And notice on the top, the x cancels because we have positive x, negative x. And we have negative 4, positive 4. Same number, opposite sign, these guys cancel. Leaving us with just a negative h on top. So the limit as h equals to 0, negative h on top. On the bottom you have x plus h minus 4, x minus 4, and then times h, because we still have this h over here. Notice that the h is cancelled, so we're just left with negative 1 on top. And we no longer have, at this stage here, if you were to evaluate the limit and replace the h with zeros, you would get 0 over 0. So we have an indeterminate form, it's not good enough. Now that we cancelled out the h's, we have negative 1 on top, so you won't have 0 over 0 because the numerator is a negative 1. So we could evaluate this now. We could replace our h with 0. This is why I said not to distribute the bottom, because all you're doing now is you're substituting the h with 0, and this is easy to calculate. All you get is negative 1 on top, and if this is 0, you have x minus 4, and then times x minus 4, which is essentially x minus 4 squared. Okay. And this is the derivative. So we found f prime of x. Great. So if it was asking us to find the derivative, we're done. But it's not. It's asking us to find the slope of the tangent line. So we have one extra step to do. And this is what I was contemplating at the beginning. Should we do it all in one shot or in 2 steps? Maybe in the beginning it's better to start and do it in 2 steps. So start off by finding the derivative first, and then after find the slope. So don't forget to find the slope. So what we're going to do now is come back to this piece here and find f prime of a. So the slope of the tangent line, let's call it m tangent. So really here before I should have left it at just f prime of x, not f prime of a. But m tangent now is just saying f prime of a. Okay, so if this is f prime of x, what it's saying is substitute the x, replace the x, well, what a is? Well, a is 5. This is f prime, a is 5. So it's telling us to plug in 5 into our function. So we're going to have negative 1 over, instead of x, it's 5 minus 4, all that squared, giving us negative 1 on top. 5 minus 4 is 1, 1 squared is 1, so negative 1 over 1. So the slope of the tangent line is negative 1. Okay. So it's at this value here, when x is 5, it's coming downwards. Okay. So I hope this helped. Let's take a look now at the equation of a tangent line. So here we have the definition of the equation of a tangent line at a given point a and f of a. This is essentially your x and y. I won't call it x and y, I'll call it a and f of a. So at some point we use the equation t of a, so t subscript a, this is for the tangent line, it's equal to f prime of a times x minus a plus f of a. So here the f prime of a, as we saw in a previous example, this is the slope. F prime of a is just the slope of a line. So this is an actual value, it's a number that you get when you plug in f prime of a. Whereas when you plug in f prime of x, this is a function. F prime of a is a number. Specifically the slope, the rate at which the line is increasing or decreasing. X minus a, so the a over here is the point that's given, the x value of the point that's given, and f of a is the y value of the point that's given. And from that we create our equation of a line. You don't have to use this formula. This is typically what's used, but at the end of the day you could also use just simply y equals ax plus b. So once you find the slope, you have your a, and then you have to go find your b by plugging in the point x and y, like we saw in high school. So this is analogous. I would get into the habit of studying this form because it shows up later when we see linear approximations. So I think it's better to get accustomed to this form, but you could also use this. It's the same thing. Okay, so let's take a look at an example. So in this example here, it says to use the limit definition of a derivative to find the equation of a tangent line. So not the slope of the tangent line, the equation of a tangent line. At the point 9 and 3, so we could think of this as a and f of a. And they give us the function f of x equals the square root of x. So let's go ahead and do that. The first thing I would do is write the formula. So the equation of a tangent line is f prime of a x minus a plus f of a. And let's go ahead and start off by essentially a and f of a, we're done. We have that. A is 9. This part's done. And f of a is done. We have our 3. These two guys are done. What we have to go get is our f prime of a. So the first thing I would do is start off by finding the derivative, f prime of x. Let me write x this time. Using the limit definition, because it's forcing us to. The limit definition of a derivative. So we have no choice. Limit as h equals to 0, f of x plus h minus f of x, all this over h. Okay. So f of x plus h, if f of x is the square root of x, we have to figure out what f of x plus h is. Okay, so at this point you guys should be comfortable with the idea of composing functions. Well, it's not really a composition, but yeah, you can think of it as the composition. F of x becomes square root of x, but now in the bracket we have x plus h. So in the square root we have x plus h, right? Everything that's in the bracket comes here, so everything that's in the bracket comes inside the bracket. Okay, so that's done. So we have the limit as h tends to 0. F of x plus h is the square root of x plus h minus the square root of x. All this divided by h. Okay. So at this stage, we're stuck. If we substitute the limit with 0, at this point, we're going to get square root of x minus square root of x, which is 0. And on the bottom, we're going to get 0. So we have an indeterminate form. We have to do something. How can we manipulate this or simplify this? So if we see square roots, one of the first things that should come to mind is multiplying by the conjugate. And that's the key to solving this problem. So we saw this in our earlier videos, and now we apply it. So we're going to multiply by x plus h, where we have our two terms. We're going to switch the minus to a plus. Okay. And we're going to multiply this on the top and the bottom, right? Because if we multiply just on the top, we're changing the function. If we're multiplying it on the top and the bottom, it's a fancy way, like this divided by this is 1. Anything divided by itself is 1. So it's a fancy way of multiplying by 1. So we're allowed to do this. Okay. So my other advice here is do not distribute the bottom. Leave the bottom as is. Okay. Focus on the top. You have a binomial times a binomial. So here you're going to FOIL. So if we FOIL, what we get is the limit as h tends to 0. Keep in mind that the square root of x times the square root of x is x. Whenever you're multiplying two terms inside a root that are the same, well, essentially like the roots cancel. So you have square root of x plus h times the square root of x plus h. So all we're left with is x plus h. Okay, that was the first term. The next term is going to be square root of x times square root of x plus h minus square root of x times square root of x plus h. Okay, so the next two terms, you always get the same thing, opposite signs. So these are essentially going to cancel. And then lastly, we have negative square root of x times square root of x. So we get just minus x. Okay, this is done. On the bottom, as I said, let's leave it. So we're just going to leave it as h times, in brackets, square root of x plus h plus square root of x. So we said before this term is going to cancel with this term. That's done. And notice here we have minus x, and then here we have positive x, same number, opposite sign. They cancel. So all we're left with on top is a h, and on the bottom we have our h. So even the h's here cancel. Okay, so let's go ahead and write that. So limit as h goes to 0, h on top, h on the bottom. This is why I told you not to distribute, because you might get stuck. But now that you see the h's are both sitting in the front, we could cancel them. Okay. And now we have the number 1 on top, so we won't get an indeterminate form. And on the bottom we have square root of x plus h plus square root of x. Okay. This gives us 1 over, if we replace the h with 0, we have square root of x plus square root of x, so we get 2 square root of x. Okay. And this is the derivative. This is f prime of x. Great. So we found f prime of x. That's done. But we want f prime of a. And we stated that a is equal to 9. So to find f prime of a, which is in our case f prime of 9, we're going to plug in the number 9 into our function, giving us 1 over 2 square root of 9. Square root of 9 is 3. 3 times 2 is 6, so we get 1 over 6. Okay. So that's the slope. I'm going to have to erase to give myself some room. And we are essentially finished, because we have everything. So the equation of the tangent line, TA, is equal to f prime of a, which we just solved down here. We got 1 over 6. X minus our a, which is in this case 9, so x minus 9, plus our f of a, which in this case the point is given to be 3. If they didn't give us this point, we could go ahead and find it. How? Just by plugging your a into the function. So they didn't have to give us the point 3. We could have solved for it by plugging into the initial function that's given. So square root of 9 giving us 3. Okay. And this is the equation of the tangent line. We're done. Okay. If you use the other formula, if you use the formula y equals ax plus b, or mx plus b, this works as well, but the answer you're going to get is 1/6 times x. So essentially, if you distribute the 1/6, you get 1/6 times x, and then negative 9 over 6 plus 3. Okay, so times this by 6. On top, you get 18 over 6. So you would have gotten x over 6 plus 9 over 6, which could be reduced, divided by 3, 3 over 2, plus 3 over 2. So if you got the answer on your own and you got y equals x over 6 plus 3 over 2, that's fine as well. Okay, awesome. So I hope this helps, and keep practicing.